Hello everyone, my name is Sitthichai Pinkanjanarod. I'm from High Energy Physics Theory Group, Chulalongkorn University, Thailand. Today I'd like to talk about massive neutron star with holographic multiquark cores and their tidal deformation. Well, it is known that nuclear matter at low temperature and low baron chemical potential is confined to hadrons, which can be described by the chiral effective theory or CET. On the other hand, very high temperature or very high baryon chemical potential, interaction between quarks becomes weak and completely deconfined, which can be described by perturbative quantum chromodynamics or PQCD. I will focus on exotic nuclear matter called multiquark, which is deconfined, strong-coupled, non-perturbative, and bounded by gravity. It is found that multiquark matter is difficult to be described by non-PQCD. Therefore, we use equation of state of multiquark from the holographic model to interpolate between low and high density. We found that high density multiquark is preferred over free quark matter, while at low density there is first order transition from low density multiquark to nuclear matter, which can be shown in the lower diagram here. Our main important results can be summarized as follows. The figure on the left shows the mass radius relation of the pure multiquark star and massive neutron star with holographic multiquark cores. The two curves on the left represent pure multiquark star of different energy density scales, while the two curves on the upper right represent massive neutron stars with holographic multiquark cores, where the blue curve represents neutron star consisting only of CET nuclear matter at low density. The figure on the right shows relations between tidal deformation and stellar masses. We found that a pure multiquark star represented by that curve here have lower tidal deformabilities comparing to that of a massive neutron star with holographic multiquark cores, which were represented by the solid curve over here. Notably, our results are consistent with our observational constraints from our gravitational waves and relevant pulsar detections. Finally, a dynamical stability of the holographic multiquark core was studied through the radio pulsations. Eigenfrequencies from the 0th mode to the 5th mode were plotted against the masses, as shown in the figure here. We found that instability of the 0th mode appears when the central density exceeds the critical value at the maximum mass.